Hi there, Physics 131. Welcome back from your break. So we're finishing off Chapter 8 this week, which is all about torque. Section 8.5 is just called Skills for Analyzing Situations Using Equilibrium Conditions. So once again, it's those three equations of balancing the two components of the forces, and the third one is balancing the torques. So, and there's a lot of biology examples in this one. So this is talking about triceps and biceps, which are in your arm, both attached to your forearm and applying a torque which rotates around your elbow joint. And so using the biceps to lift, you can model the forearm as your system, draw a little dashed line around that system, and then you've got all these forces acting on it. And once you define a rotation axis, which I think is going to be probably the shoulder in this case, the elbow. Elbow is axis of rotation, then all of these forces exert torques around that axis, and you can balance the torques with sum of the torques equals 0, and balance the forces in the y direction with the sum of the forces equals 0, and you can solve for all of these forces. Standing on your toes, so it talks a little bit about your Achilles tendon. Again, you have to choose a rotation axis somewhere to apply the conditions of equilibrium. Lifting from a bent position, so this shows a bad way to lift, and you can model that person as being like an L beam where I guess your hip here is the axis of rotation, and you've got a back muscle which is pulling upwards in order to lift. There, it's pulling to this angle of 12 degrees in order to lift this thing. So when you work out balance all the torques and everything, and balance the x and the y components of the forces, you end up with the tension being on your back as being 2,380 newtons. That's 540 pounds. The back muscle exerts a force more than 4 times the gravitational force that Earth exerts on the person, and that the discs of the lower back are compressed by a comparable force. So that's why it's such a bad way to lift that way, and they give you a better idea. If you straighten out, then there's a lot less strain on that muscle. So it's a good way to hurt your back is to lift the wrong way. So review that. And the last section is called stability of equilibrium. So this is all about equilibrium and tipping objects. So it's the gravitational torque here. So for example, it talks about balancing the subway, and when you're standing, it's again as if the gravity reaches out to your center of mass to pull you down. So, and it's important that gravity, when it pulls you down, doesn't exert a torque around any possible rotation axis which will rotate you. So what you do is you produce a base, which is 2 feet from the base of the object, and if the bottom of that base is directly below the center of mass, then the 2 possible rotation axes, which is the edges of the base, no matter which one you choose, gravity produces a restoring torque. If the center of mass is outside that base, like on one side, then that torque will produce, a tipping torque around the outside of that base, if that's the rotation axis. So for example, this person's foot on the left here, if the gravity center of mass is to the left of that left foot, then that becomes a rotation axis, and gravity produces this counterclockwise torque, and the person falls, whereas this person recovers. So this is the rule, is that the center of mass is somewhere over the base. So for example, right here, when you tilt the box slightly, you perturb it one way, gravity restores it. But if you tilt more and more, there will be a tipping point where the center of mass is directly over that edge of the base, and then it starts to tip to the other side. So you can find that angle. Here's the Leaning Tower of Pisa in Italy. The center of mass is again over the base, and that's why the whole thing doesn't tip over. But there'll be some maximum angle. If it was over here, then the whole thing would tip. So that's a little bit about perturbation. It leads to this figure 8.23, which I'd refer you to. This is about stable, unstable, and neutral equilibrium. basic idea here is stable equilibrium. For example, there's the ruler which is supported by the top of the nail. If you make a little perturbation to the ruler, like knock it one way or knock it the other, then gravity tends to restore it to its original position. That's called a stable equilibrium. It accelerates back to where it was. If they put the nail on the bottom and hang it this way, I guess you could kind of balance it right there and you'd hope it just stays there, but any tiny little perturbation is going to cause it to rotate around, right? So that's called unstable equilibrium. You can imagine an equilibrium where the torque to center of mass is directly above this, but any perturbation will cause it to accelerate away from its equilibrium. And then neutral equilibrium, they put the nail at the center of the ruler, and the idea is that if you accelerate it a little bit, or perturb it a little bit, it doesn't want to accelerate one way or the other. It just can maybe go at a constant rotational velocity or something. So a pencil that's balanced, on your finger, that's again unstable equilibrium. Here's a trick where a person is riding on a tightrope, but hanging below him is another person. Well, what this does is actually brings the center of mass below the bicycle. And so it looks pretty unstable, but in fact, as a system, these two people together form a stable equilibrium, because once again, the center of mass now is below the rotation axis, and then you have a stable equilibrium. So it's a little party trick there. Tipping the vending machine. This is a typical problem where you have to find first, what is the horizontal pushing force you need to exert to get just these front feet off? And then B is, at what critical angle would the whole thing fall forward? So I would work through that. It's a little bit of geometry, always remembering that the center of mass is at the sort of geometrical center of a typical homogeneous object. So take a look through that. You end up using the inverse tan function a lot. It's a nice little warning sign. Don't tip or rock the vending machine. And that's it for chapter 8. There's a nice little summary here at the last page. Again, how we defined center of mass. There's the equation for the x and the y coordinates of the position of the center of mass. Not a difficult equation. What torque is. So torque is this force times the lever arm, L sine theta. So static equilibrium is when you have these three equations, which is the sum of all the forces in the x direction equals 0, the sum of all the forces in the y direction equals 0, and our new third equation, which is the sum of all the torques around some rotation axis equals 0. And then lastly, this equilibrium. So idea is equilibrium, the equilibrium of a system is stable against tipping if a line through its center of mass passes through the area of support. And the equilibrium of a system is stable against rotating as long as the center of mass is below the axis of rotation. And that's it for chapter 8. And next class, we'll get into starting into chapter 9. Okay, bye for now.